In this video, we're going to look at some nuclear chemistry reactions. So nuclear chemistry reaction involves taking a nuclei and changing it into something else. There's several different ways you can accomplish this. So we're going to have to know some particles here. So let's go through a few. We've got the alpha particle. It looks like a helium atom, except it has no electrons, so it's got a +2 charge. A beta particle is actually just an electron, so it's got a -1 on the bottom here. So let's be careful of this as we proceed. A gamma particle, now this one is just all energy. It's got no mass or charge. We've got a proton. So we got a couple of symbols here for a proton. You can have that, or you can have this one that's exactly like a hydrogen, except it wouldn't have an electron with it. So the proton would have a +1 charge. A neutron would have, again, a massive 1 and no other subatomic particles, so no charge. And a positron that I like to think about as being a bizarro electron. Notice it's exactly the same, except now it has a +1 charge to it. So let's take a look at some types of reactions. So the first one, there are 4, would be a decay. And that's where a nuclei likes to boot off a subatomic particle to become more stable. And we're talking subatomic particles, we're talking about the ones we just saw on the previous slide. So it could be those 6, could be some other ones, but those are the ones we're going to focus on. So an alpha particle, alpha decay, is emitted by the nuclei because it wants to become more stable. So let's take a look at an example here. Uranium-238. So it is kicking off an alpha particle. Now it's going to be our job to balance the numbers here. So on the left side of the arrow we have a 92, and on the right side we have a 2. So what plus 2 would be 92? The answer should be 90. So you go to your periodic table, you look up the element that is number 90, and it should be thorium. And then we're going to do the same on the top here. We've got 238 on the left side, we've got 4 on the right side. So 238 minus 4 should give us 234, and that would be alpha decay. Let's take a look at some beta decay now. So again, beta decay is essentially an electron is emitted by the nuclei to become more stable. So what if thorium-230 were to undergo beta decay? All right, so let's be careful here. On the left side we have 90, on the right side we have -1. So what number plus -1 would be 90? And that would of course be 91. And the 91st element on our periodic table is protactinium. Up top here we've got 230, we've got 0, so that must still leave us with 230. On to gamma decay. So now remember, gamma is just, it's this particle that's all energy. So if an atom just gives off a gamma particle, nothing's going to change. So there's another subatomic particle that's going to be included, whether it's a beta particle or an alpha particle. Okay, so let's complete this gamma decay question here. We've got iodine undergoing gamma decay. So there's a gamma particle, and in this question, it's also going to be giving off an electron. So we have 53 on the left, -1 on the right. What number plus -1 will be 53, and that should be the 54th element, is xenon, and it looks like it should be 131. All right, well, let's look at a second type of reaction here. This is called a transformation or a transmutation, and all that is one element's going to get changed into another. This is kind of the classic example, was Ernest Rutherford changing a nitrogen-14 into a oxygen-17. So how he did that was with an alpha particle. So we've got our nitrogen here, we've got our alpha particle, and the question is telling us that oxygen-17 is produced, and we want to know what the missing number is here, the missing particle. So let's take a quick look. Left side we've got 7, we've got 2, and that should be 9. Over here we've got an 8. So what number plus 8 should give us 9? Of course that's 1, and that would be a hydrogen. And just to check the top numbers here, we've got 14, 4 makes 18. And 17 and 1 also makes 18. So again, this transformation, what's really happened here is this nitrogen has been transformed into this oxygen. There's our nuclei, and it's been done via 2 subatomic particles. So I guess you have to differentiate the subatomic particles from the nuclei. Let's take a look at another one, nuclear fission. So fission takes a heavy nucleus and breaks it into 2 smaller ones. So what do we got here? We got uranium, and it's breaking up into this barium here. So again, we'll have to do the math. 92 minus 56 should be 36. Our 36th element is krypton, and up top, 235 minus 141 should give us 92. The creation of nuclear energy uses this process with the aid of a single neutron. Here's a classic example from a nuclear reactor. You've got uranium-235 hit by one neutron. It will make these two elements, and it'll actually make 3 more neutrons plus a bunch of energy. And then these 3 neutrons, what they're going to do is they're going to go find more uranium, 3 more uranium particles, and the whole process continues. So you only need 1 neutron to start this process going, because you'll have 3, 9, 27, and so on for neutrons that are going to continue this reaction. Let's take a look at our last one, fusion, fusing 2 nuclei together. So if we had this example here, this one should be straightforward. 6 and 6 makes 12. And up top here, we've got 12 and 12 makes 24 and 23. So our missing particle could have been this one here, kind of sped past a bit, but 23 and 1 makes 24. This is what's going on inside of our sun. We've got nuclear fusion happening. I've got some questions here, so you can pause the video. There's 2 on this slide and 3 on the next. Take a look at these. The answers will be provided at the end of the video. Thank you for watching.